So in this last video of section 4.4, I just wanted to summarize what we've been talking about and then go through some examples. So this is a good place to summarize everything. So these first two indeterminate forms are the forms we want for L'Hopital's rule because they're already in terms of a fraction. If you are given a product, you can always change a product into a fraction by taking f of x times g of x and rewriting it as f of x over 1 over g of x. Okay, or you could do vice versa, or you could take g of x divided by 1 over f of x. Good. And then what did we do for the infinity minus infinity situation? We multiply by a conjugate, or in terms of trig functions, right, we rewrite in terms of sines and cosines. Good. And then, so this is kind of a case where we don't have a really obvious substitution that we can always make. But in this last case we do. If you have f of x times g of x, or f of x to the g of x power, you can always rewrite that by taking the logs first. And so we would find the limit of the log of f of x to the g of x power, which means you're finding the limit of g of x times the natural log of f of x. And of course this is a product, right? And so from what we said up here, you can change the product into a quotient by taking, for example, the limit as x goes to whatever of the natural log of f of x. You probably want to keep that one on top, and then you could write 1 over g of x down below. Good. And then once you find that that's equal to some limit L, then you can go back, and that was a two-step process. The limit is e to the L then, right? Good. So those go together. All right. So those are the kind of algebraic manipulations that we have in this section. I just wanted to try out one more example, and so I'm going to couch this in a question. Find the error. And so we have the limit as x goes to infinity of x squared plus the sine of x divided by x squared. Okay, and so I go through and I check, and this is let's see, infinity over infinity, and so this is a form that I can use L'Hopital on. And so I take the limit as x goes to infinity of 2x minus or plus cosine of x divided by 2x. And this is still infinity over infinity form, right? So we can use L'Hopital again. We have the limit as x goes to infinity of 2 minus the sine of x divided by 2. Good. And now what's the limit as x goes to infinity? Well, another way to write that would be like 1 minus, let me rewrite that. That's the limit as x goes to infinity of 1 minus 1/2 sine x, right? And this just oscillates back and forth. And so this expression will never settle down, and so this limit does not exist. So therefore the conclusion is the limit does not exist. False. That's not the right conclusion. Why isn't it the right conclusion? We said that the limit, we said that you could use L'Hopital's rule as long as your limit actually gives you something, actually exists. Because now let's go back to the original expression and let's take another look at it. Let's see, we have x squared plus sine of x divided by x squared. Notice that you could rewrite that as the limit as x approaches infinity of 1 plus the sine of x divided by x squared. And now we know that the limit of 1 exists. How about the sine x over x squared? Well, remember the sine x divided by x squared. Do you see the setup? Do you remember this from our, what am I setting up here? The squeeze theorem. What's the biggest possible number the sine can possibly be? It is a 1, so I'm going to replace the sine by a 1 and make it bigger. And similarly, I'll replace the sine by minus 1 and make it smaller. And now as x goes to infinity, this goes to 0, this goes to 0, and so therefore this must also go to 0 by the squeeze theorem. And so therefore, if we go back to our limit, we see that the limit is 1, and the limit does exist. Good. And so I wanted to bring up this example because this is an example of something where L'Hopital's rule fails, if you will. It doesn't really fail because the theorem rules this case out. But you do have to be careful. If your L'Hopital's rule leads you to an expression where the limit does not exist, that means you have to go back and work on the original expression again. Okay, so if you get a limit that does not exist, L'Hopital's rule may not or does not apply. Good. All right. So maybe I'll pause here and just work through a couple of extra exercises. Okay, so let's take a look at number 54 in the book. And that is, we're taking the limit as x approaches 1 from the right of the natural log of x to the 7th minus 1 minus the natural log of x to the 5th minus 1. Good. All right, so taking a look at this, if we're approaching 1 from the right, that means each of these logs is going to the log of 1 minus 1, which is 0. And so that is minus infinity minus minus infinity. Okay, so minus infinity plus infinity is our indeterminate form. Okay. And so let's see. I'm trying to get to a fraction, right? Is there any way I can get to a fraction from this? Remember that the log of a minus the log of b is the log of a over b, right? And so we can get to a fraction from that. Very good. And now, what can we do with this? Well, remember that if your function is continuous, then you can bring the limit into the expression, and so this becomes the log of the limit as x approaches 1 from the right of x to the 7th minus 1 over x to the 5th minus 1. Good. And now this expression here is ready for L'Hopital, right? Because we got a 0 over 0 form. So that's going to be the log of, excuse me, let's see, 7x to the 6th divided by 5x to the 4th. Oops, I still have my limit here. And so we can apply L'Hopital again, right? And so, in fact, we can apply L'Hopital several times, right? Oh, wait a sec. Can I apply L'Hopital again? I was just thinking about making this infinity instead of 1. Yeah, this is actually, the limit exists, right? The limit here is 7/5. So this is the natural log of 7/5. Good. All right. Let's try another one. This one's a little bit tricky, so maybe we should do it together. This is number 53, and we're given the limit as x goes to infinity of x minus the natural log of x. Good. Now, if I think about this problem, I think in a section a while back, didn't we prove that x was bigger than the natural log of x? And so you might expect this to actually blow up on you, and in fact it does. But let's see if we can prove that somehow. I need to make this a fraction. So one way I can make it a fraction is kind of a weird factorization. How about if I factor x out of this expression? Then what's left inside? I have 1 minus, and then what's the other term? Well, that'll give me a natural log of x over x, and there's my fraction. Good. And so now I'm able to rewrite this. Let's see, what is the limit as x goes to infinity of the natural log of x over x? Well, it's going to be the limit as x goes to infinity. Can we use L'Hopital? Sure. 1 over x divided by 1. And it looks like that's going to 0, right? And so therefore, we have something. If we take a look at this form, then this is going to be this is going to be infinity times 1, right? Because this is 1 minus 0. And so what does infinity times 1 go to? That does go to infinity. And so this limit does not exist then. Okay, so this was kind of a tricky one because it's an odd, non-standard way of expressing the expression. All right, so give the other problems in section 4.4 a try, and you'll notice that there is a lot of algebra here, so that'll be actually some good algebra practice for us. All right, I'll see you in the next section.